Welcome to part 2 of tutorial 1. In this video we will learn about the remaining subsets of real numbers, that is, rational and irrational numbers. Are you ready? Let's go! The word rational is linked to the word ratio. Hence, rational numbers are numbers that can be expressed as a ratio or quotient of two integers. As a general example, consider two integers p and q. A rational number is the ratio of these two integers, shown here as the fraction p over q, where q cannot equal 0 because we cannot divide something by nothing. When a rational number is converted from a fraction into a decimal, the result can be either an integer or a terminating decimal, that is, a decimal that has on the right-hand side of the decimal point digits that do not continue forever, or a recurring decimal, that is, a decimal that has on the right-hand side of the decimal point a digit or a sequence of digits that repeats forever. Let's look at some examples. Example 1. Consider 12 over 2. This is a rational number because it is a ratio of two integers, 12 and 2. When converted into decimal form, 12 over 2 equals 6, which is an integer. We can also express 6 as a ratio of itself and 1, as shown here. In fact, every integer can be expressed as a ratio of itself and 1. Therefore, integers are included in the set of rational numbers. Example 2. Consider 5 over 8. This is a rational number because it is a ratio of two integers, 5 and 8. When converted into decimal form, 5 over 8 equals the following. This is a terminating decimal because on the right-hand side of the decimal point, there are digits that do not continue forever. Therefore, 5 over 8 is definitely a rational number. Example 3. Consider 2 over 3. This is a rational number because it is a ratio of two integers, 2 and 3. When converted into decimal form, 2 over 3 equals the following. This is a recurring decimal because on the right-hand side of the decimal point, there is a digit, in this case 6, that repeats forever. Therefore, 2 over 3 is definitely a rational number. Other ways of expressing this recurring decimal are as follows, where the dot or bar above the 6 indicates that this digit repeats forever. Example 4. Consider 4 over 7. This is a rational number because it is a ratio of two integers, 4 and 7. When converted into decimal form, 4 over 7 equals the following. This is a recurring decimal because on the right-hand side of the decimal point, there is a sequence of digits, in this case 5, 7, 1, 4, 2, 8, that repeats forever. Therefore, 4 over 7 is definitely a rational number. Other ways of expressing this recurring decimal are as follows. In the first case, we place a dot above the first digit and the last digit in the sequence to indicate that this sequence repeats forever. In the second case, we place a bar above the entire sequence, again to indicate that this sequence repeats forever. We can represent the set of rational numbers with the mathematical symbol shown here, a double-struck Q. Let's also represent the set of rational numbers on the Venn diagram we created earlier. Given that rational numbers include integers, we can illustrate the set of rational numbers by drawing a set that contains the integers, and we can label the set using the double-struck Q symbol. Also, given that rational numbers include ratios of integers that can convert to terminating decimals, for example 5 over 8, or ratios of integers that can convert to recurring decimals, for example 2 over 3 and 4 over 7, and given that these are not integers, we place these numbers in the green space only. Now, what you see on this Venn diagram can be written as the set of natural numbers is a subset of the set of whole numbers, which is a subset of the set of integers, which is a subset of the set of rational numbers, which is a subset of the set of real numbers. Great! Let's now conclude this tutorial by talking about irrational numbers. Irrational numbers are all of the other real numbers that are not rational. That is, all of the other real numbers that cannot be expressed as a ratio of two integers. When an irrational number is expressed in decimal form, the decimal is both non-terminating and non-recurring. Let's look at some examples. Example 1. Consider Euler's number e. In decimal form, this equals the following. This decimal is both non-terminating and non-recurring because on the right-hand side of the decimal point, there are digits that continue forever, and there is no digit or no sequence of digits that repeats forever. Therefore, Euler's number is definitely an irrational number. Example 2. Consider the number pi. In decimal form, this equals the following. This decimal is both non-terminating and non-recurring because on the right-hand side of the decimal point, there are digits that continue forever, and there is no digit or no sequence of digits that repeats forever. Therefore, the number pi is definitely an irrational number. Example 3. Consider the square root of 3. In decimal form, this equals the following. This decimal is both non-terminating and non-recurring because on the right-hand side of the decimal point, there are digits that continue forever, and there is no digit or no sequence of digits that repeats forever. Therefore, the square root of 3 is definitely an irrational number. Given that irrational numbers are all other real numbers that are not rational, we can represent the set of irrational numbers as the difference between the set of real numbers and the set of rational numbers, as shown here. The set of real numbers minus the set of rational numbers. The backslash symbol represents difference or minus when operating with sets. I will cover this in more depth in a future tutorial. Let's now return to our Venn diagram for the last time to illustrate the set of irrational numbers. We can illustrate the set of irrational numbers by drawing a circle within the set of real numbers but separate from the set of rational numbers, and we can label the set using the double-struck r/double-struck q expression, which once again is read as the set of real numbers minus the set of rational numbers. We've made it to the end of this tutorial on real numbers. Thank you very much for your attention. If you found the videos in this tutorial helpful, please be sure to like them and please subscribe to our channel so that we can continue to produce more. All the best and see you next time for more fun and learning.